I'm going to kind of give you kind of a little bit of math lessons, and in particular, I'm going to show you kind of how to turn calculus into algebra, or like maybe another way to look at this is to kind of eliminate all intuition and turn this into just symbol pushing. That is all I can handle with my peanut science brains. That's how I like to do math. I just calculate by pushing symbols around. Now, there's nothing new here. Everything here has been done by people that are way smarter than me. All I'm doing is being the messenger, trying to take what they do and phrase it in something that can, maybe normal people can understand. Now, I don't know about people here, but like since COVID, I've been having really kind of weird dreams. And one recurring dream that I had was that I kind of somehow skipped math classes, or I just completely forgot about it. And these dreams were so realistic, actually, that when I wake up from them, I really have to remind myself, yes, I did graduate. And this is kind of this is not true. This is fake dreams. But since all these dreams were about math, I thought, okay, let me just kind of do some revisit some of the kind of math to make sure that I do understand it, and maybe then those dreams go away. Now, the reason I picked calculus is because in a previous talk I predicted that software 2.0, which is instead of writing software, you learn software from data, like machine learning. That would be a combination of differentiable programming and probabilistic programming. Now let's kind of zoom in a little bit here. If you look at differentiable programming, it's kind of obvious, right? It's about differentiation. And what is kind of why is that? Well, if you want to differentiate a program is kind of composed out of functions or out of statements, but it's kind of composed out of smaller things. And in order to kind of differentiate to a complex program, you use something like the chain rule to get differentiate through that. And here I just kind of copied here from Wikipedia the chain rule, and you already see kind of it has lots of weird notation with D and like fractions that are not fractions. Probably you can all remember this from from your math classes, how does this kind of even work? And then when you zoom in even more and to kind of say what is kind of the derivative of a function, it's kind of defined with this scary stuff here, the derivative f prime of a function f is the limit of h going to 0 of f8 plus h minus fh divided by h. Ooh, so there's a lot of kind of complex things here. Now zooming in, double clicking on limit again, now we get here the kind of typical epsilon delta definition of limits. And at this point, I think most people's brains just explode or melt, or people kind of grab a beer or maybe something stronger. And it's wow, this is kind of super complicated. Now, if you look at probabilistic programming, that is all about integration. And maybe that's a little bit surprising. So let's kind of zoom into that a little bit. Why is probabilistic programming about integration? Well, if you look at the kind of probabilistic programming is really kind of programming in the probability monad. So your side effects is uncertainty. So just like in Haskell, you have the IO monad or the list monad. Here you have the probability monad, and now your program kind of returns a probability distribution. And if you look at the bind of this monad, it has this kind of big integral in here. And if you look at this paper, it even says not only is this integral confusing, but the notation is also confusing. Now I know that probably there's people, and even now in the Haskell community, people don't like monads anymore. It's algebraic effects and applicatives and whatever. So in case you don't like monads, Here's another way where you can see why with probabilistic programming you need integration, because if you're talking about a probability density function, in order to turn that density into a probability, you have to take an integral. So you want to compute the probability that x is between a and b, then you have to take the integral from a to b of whatever the PDF is. In this case, it's a Gaussian distribution. And if you ask what is the probability that x is c, then that is 0, because it's a density, not a probability. So in order to turn a density into a probability, you have to do integrals. Now let's look at, double click on what integrals are. Well, integrals, and the previous picture already showed that, is the idea there is that you compute the area under the curve between 2 points. And I see here already there is already they're talking about limits again. And if you double click again on this definition, you see what people do is you slice up this interval into tiny rectangles, and then you sum them up, and then in the limit this you get the area under the curve. But again, it's even more epsilons and deltas, and that's exactly what I want to avoid. So I want to I want to turn this into something where we don't have to care about epsilons and deltas, and we turn everything into just simple pushing, where we can turn off our brains and just use functional programming techniques to find answers to our questions. All right, so here's the where we are. So software 1.0, that's what we're all used to. There's discrete, we are computing exact results, and it's all based on algebra, the algebra of programming, or whatever you want to call it. Now, if we're moving to this new world of software 2.0, we are changing from discrete to continuous. We're changing from exact to probabilistic, and we're changing from algebra to calculus. And it's this last thing that I don't like, because as I said, I like algebra, I like just manipulating symbols. So the whole goal here is to show that we can reduce calculus to algebra, and that we don't need epsilon and deltas, we don't need limits, and everything really just boils down to basically what we always do when we do regular functional programming in the squiggle or Burt-Merton style. So don't worry, everything will be all right. So let's talk a little bit about the real numbers. Because mathematicians, it took mathematicians I don't know, centuries or a long time to actually define what real numbers are. And from if I'm just being a little bit blunt, you can see this as a an abstract data type, right? You define a set of values, you define some operations on them and some laws, and now you have defined your algebraic data type. But there's nothing special about the real numbers. In some sense, the real numbers are kind of weird, right? Because they are uncountable, so there's a lot of them. And most of them you cannot even ever express, because there's way too many of them. If you look at comparison of real numbers, that's undecidable. So they are a pretty crazy abstract data type, but it's very convenient for doing math. Now, since if this is an abstract data type, why would we stick with this version of reals? And we don't have to. So here's another version of real numbers, and this is the William Lauver. This is synthetic differential geometry. It is defining another set of real numbers with some different axioms. And I would like you to get like in particular look at kind of like axiom 4 here. And axiom 4 here says that like, it assumes that there is a kind of like a subset of values in R for which the square of these values is 0. A fancy way to say is that that's got nilpotent infinitesimals. And then this axiom here is kind of like super important. It just says that for every function from D to R, there is a unique A such that like, f of D equals f0 plus D times A. And this axiom really captures what is a derivative of a function. So really what this axiom says is that like, every function has a derivative. And this derivative is that kind of like that unique value A. And we'll see kind of like, that's what this talk will be about. We'll kind of like, zooming in on that and kind of like talking about that. Now, of course, when we define a set of axioms, we need to have a model, right? We need to make sure that these things kind of like, exist. And this is where we are getting into some weirdnesses and like, a lot of paradoxes. Just to get like, make sure that you understand like that we distinguish between these two different real numbers. So the double struct R, that is the kind of like, the traditional real numbers. I'll also use them later for floating point numbers. I know a lot of people don't like that, but I just do it anyway. And then the kind of the regular R, those are Larver's reals. So just kind of like make sure that we are using different R's for these two different kind of reals. Now here's the thing: if we get like assume that we are in the real numbers. And we got like, assume that like, there's a nilpotent infinitesimals, then for the regular real numbers, the only value for which like, D squared, the only value D for which D squared equals 0 is 0. All right, so that's kind of like if we take the regular real numbers. Now, if we got like, look at these two calculations, we now have two ways to write f of D. Because if D is 0, we can write it as 0 plus D times 1, or we can write it as 0 plus D times 0. But if you remember from axiom 4, it says there's a unique A that makes this equation true. And so by uniqueness, it must be that 0 equals 1. So if we get like, assume axiom 4, and the real numbers, now we get a kind of like, a paradox, a contradiction. So these are not compatible with each other. Now let's look at another example here where we are looking at the other real numbers, but now we're defining a function that uses a case distinction. So the function here, f of D, is just saying like if D equals 0, then return 0, else return 1. You would expect like, that's, I mean, we're writing functions with conditionals all the time, right? So in this case, we assume that the set of infinitesimals is not 0. So now we can kind of like, compute here that 1 equals D times A. Just by applying the axiom and doing some arithmetic and we know that f0 is 0 because we defined f like that. But if we then multiply each side by D, now we get that 1 equals 0, or sorry, D equals 0, and we just assumed that the set D was not equal to 0. So we have here another contradiction. So where we are at is that if we are in the Larver's reals, we cannot do case distinction. And if we are in the regular reals, we cannot have nilpotent infinitesimals. Now the way out for this is to don't accept the excluded middle, so don't allow you to write functions that do case distinctions, and you have to go into intuitionistic logic and also all these kind of things. But as I said, I was going to keep things simple. So instead of going into like, weird forms of logic, what we're going to do is we're going to like, look at a slightly simpler type, where we get like, 80% of the benefits, where we can do all the calculations, and then later we'll see like how we can generalize again to like the arbitrary case. So what we're going to do is we're going to look at dual numbers, and dual numbers are pairs of real numbers, which have a real part and an infinitesimal part. Where the like, and the epsilon square equals 0, so that's the kind of infinitesimal part, that's a nilpotent infinitesimal. Think of these things as very similar to complex numbers, a plus bi, where I square equals -1, and here we have a plus b, a plus a epsilon, where like epsilon square equals 0. Now the nice thing about these dual numbers is that when you lift a regular function from the real numbers to dual numbers, it computes a unique dual number representing the result of the original function plus the derivative. So again, like, what is important here, and I kind of like, you will see this kind of several times in this talk, is that there's something for every function, there's a unique something, right? So this kind of like, plays a key role in what we're doing. Now here's an interesting thing, which is if you take two of these kind of like, infinitesimal parts, like a epsilon and b epsilon, then if we multiply them, that becomes 0 as well. So instead of looking just at epsilon, what we're doing is we're defining a subtype of D of all values a epsilon, where a is a real number. And those, we call those the infinitesimals. And then you can look at epsilon not as an infinitesimal so much, but more like a unit of perturbation. It's got like, it's like a unit of measure, right? It's like, a epsilon, like $8 or a euros. Except when you're kind of like, multiplying two of these kind of like, perturbations with each other, they vanished into 0. So it would be like if you multiply $2 amounts, it becomes 0. So that's the intuition here. So epsilon is not really a value, it's just like a unit that has special properties. Now, how do we kind of like prove this property? How do we prove this property of dual numbers, that when I, lift a function over dual numbers, it will compute the original function plus its derivative? Well, you can use Taylor expansion. Now, first of all, like Taylor expansion assumes that we already know what derivatives are, and that we can prove that Taylor expansion is true, which would kind of go against our whole idea of starting with like some axioms, right? So this is not going to work. Like Taylor expansion, it gives us some kind of like validity that this is not nonsense, but we cannot use this as a proof. Maybe what we can do is, since these like infinitesimals, maybe you can kind of think of them as kind of like really tiny values. Maybe we can just take that definition of derivatives that uses limits and replace the limits by infinitesimals, because they are kind of like values that are kind of like super tiny, just like h here when it goes down to 0. That is actually kind of like not kind of really great, because in that case we kind of like we cannot divide by epsilon, because once we divide by epsilon, then we can also prove that 0 equals 1. So instead, what we do is we look at these dual numbers and say, hey, really what we should do is we should say that these have structural equality. So when our two dual numbers equal, they are equal when they're like the real parts are equal, and when their infinitesimal parts are equal. And if we just kind of like drop that first kind of like lowercase a and b, then we can say when our two infinitesimal values equal, well, when the a and the b are the same. So this is called micro cancellation. And so instead of using division by epsilon, we're going to stick with this micro cancellation. So if we can show that like A epsilon equals B epsilon, then we can drop the epsilons and we can conclude that A equals B. But again, from a programming perspective, really what we're doing is we're saying that these things have structural equality. And then here on the right, there's another way to define like, you know, this micro cancellation, but it doesn't really matter for here. Now here's another kind of like, you know, problem. When I kind of like, you know, do this, now you can say, hey, but what happens here? Like, let me kind of prove that like epsilon equals 0. And I said epsilon is not equal 0, but I can prove here using micro cancellation that epsilon equals 0, right? Because I start with f of epsilon. Well, that's the same as f0 plus epsilon. So using the like, you know, the dual number property, this becomes f of 0 plus the derivative of f of 0 times epsilon. I propagate the epsilon across this, then this becomes 0. So now I've shown f epsilon is like f0 multiplied by epsilon. I use micro cancellation. So I now have proven that f epsilon equals f0 and epsilon equals 0. So that's kind of like, you know, not so smart. But, oh, let me go back here. But the thing here is that I kind of like, you know, applied kind of like, you know, micro cancellation to a value of type double and not to kind of like, you know, a real number. So it's like, you know, this is the type checker will kind of tell you that this is like, you know, bad. So we don't have to worry here. Now let's give you kind of like, you know, example here of how useful what we have done so far here is. So let's kind of like prove here that the derivative of the inverse of a function is like, you know, 1 divided by, is 1 divided by the derivative of f applied to the inverse of f applied to a. I won't go through this kind of like, you know, calculation in detail, but as you can see, it's all kind of like, you know, just standard stuff, right? Like, you know, I just apply f to both sides there. Then I use the fact that f as an f and f inverse are inverses. Then I use the dual numbers property. I use micro cancellation. So I can do all these calculations now to compute derivatives of functions without using limits and so on. And I've turned this, like, you know, all this calculus now purely into algebra. And the great thing is I don't need to have any intuition. I don't even know what the derivative is, right? I don't even think about that this is the tangent line of a function. No, it just has become like purely algebra. I just kind of like push symbols around and I kind of like reach a conclusion. And then I say, thumbs up, this is kind of like, you know, apparently the derivative of that function. Here are like, you know, some of the rules that you got like maybe learned in high school, the sum rule, the product rule, the quotient rule. You can just kind of like derive them using straightforward calculation, using simple algebraic properties like, you know, distributivity, commutativity, all super, super simple. Now let's kind of like, you know, look at something a little bit more challenging. And like, you know, this is, with math, I'm always amazed that people can like figured this stuff out like centuries ago. But if you can like, you know, do a little bit here, geometry, you can show that the like sine of epsilon equals epsilon, the cosine of epsilon equals 1, and the tangent of epsilon equals epsilon as well. And then this kind of like, you know, the triangle here shows how you can prove that. We're going to use this now to compute that the derivative of sine equals cosine. And if you look at this calculation, again, like all we're doing here is we're just using algebra. We're using the dual numbers property. then we're using like the compound angle property, where the sine of A plus B can be expressed as another sum. And then we use the fact that cosine of epsilon is 1 and sine of epsilon is epsilon. We do some arithmetic, and then we see that we have proved that sine prime of A times epsilon equals cosine of A times epsilon, and then we can use the micro cancellation to conclude that the derivative of sine equals cosine. And I hope that everybody agrees that this is like, super easy, right? Like, you just, it's regular functional programming. I'm just replacing equals by equals. I'm using some regular laws, and everything runs like super smooth. Another great thing of these dual numbers is that you can like turn them into a code very easily. So as I said, like a dual number is just a pair of values of a real part and an infinitesimal part. They have structural equality. And then if you look at the definitions here in code, it's literally got like the same, like writing in code, what I just did over there in the math. So it's like super easy. So with this, you get automatic differentiation. Now this is called forward automatic differentiation. If you want to do backwards automatic differentiation, you just turn this into continuation passing style and you're done. So they are just, there's nothing special about like backwards AD, it's just forward AD in continuation passing style. All right, now let's do a little bit more math here. And what I'm going to do is I'm going to because I still have some Haskell roots, I'm going to take this dual numbers property and I'm going to put it in point-free style. So for people that to follow along, we start with the thing in red, and we're going to encode it as the thing in yellow there. And I assure you, this is exactly the same thing, except I introduce epsilon, alpha, beta, and gamma, and these are functions that we'll introduce along the way. But now you see that the parameters are disappeared. So we're going to put this in point-free style. And the reason we're doing this, what we're using to put it in point-free style is something called Scholarsation. So with Scholarsation, we can take a formula that has existential quantifiers and universal quantifiers, and we can remove the quantifiers. So this is a trick that we're going to use here. And that's the first trick that we're going to apply. So here are a couple of examples of using Scholarsation. And what we're going to use it for, you should look at this third column here, because all our properties were of the form, for every something, there was a unique something such that some property holds. And if you look at the bottom right here, you can write this in quantifier free form as p of x comma y if and only if y equals fx, where this fx is this function f is a magic function that, given the x, will conjure up the y for which this property holds. So this is super useful. Now we don't have quantifiers, so let's use this Scholarsation to take our formula for dual numbers and write it without quantifiers. All right, so here's what happens. We're taking this formula here for all A. There exists exactly one dual number such that this property holds. So if we apply Scholarsation to it, we get this formula here. So we get basically, we turn this equality into two equalities with a an if and only if in between. Again, you don't have to understand this, just use mechanical transformation, right? I just blindly apply this rule. That's what I like. I take this formula, this column machine tells me to turn it into this. I just do it, and here we get our formula. Now let's do some Haskell style stuff to it. if we look at the kind of left side of this mutual implication, FA plus A epsilon equals B plus BA epsilon. If we introduce a function alpha, and this function alpha just kind of like, you know, takes two parameters and returns a function that takes a third parameter, multiplies the second one with that, and then adds the first one to it. You can write it using function composition, or if you really want to write it point-free style, it's this kind of weird uncurry thing that you see there. But if we kind of apply this function alpha on the kind of like, you know, on the this left side of the red side here, the left side of the mutual implication, we can just drop the A epsilon from both sides, and now we get like F compose alpha A comma 1 equals alpha A comma B. All right, so it's a little bit kind of like, you know, the little chick there is kind of like, you know, it's tongue-in-cheek. I don't think it's kind of like really much clearer, but it makes it easier to kind of like, you know, compute with this stuff. Now let's look at the right-hand side. What we're going to do there is we're going to introduce a function here to kind of eliminate this conjunction. And we do that with this combinator that takes two functions and a parameter and kind of like lifts application over this kind of like these two functions. And now we can take the right-hand side and kind of like, you know, turn that into something that looks kind of like, you know, a little bit more variable free. Not completely variable free yet. But if we kind of like now look at both sides, we have rewritten our kind of like, you know, mutual implication into something that looks already kind of like, you know, with fewer variables. Now the next thing we need to do is we need to kind of like, you know, let's go back here. What we want to do is we kind of see on both sides there's this B comma B, and we want to kind of like, you know, eliminate that as well. So that's the kind of like next kind of like thing that we're going to try to do. And for this, we need to kind of like, you know, generalize the projection function. So if you look at the projection function that takes the real part and the projection function that takes the infinitesimal part, what we want to do is we want to lift these over functions, and that's basically what beta and gamma do. And if we define them like that, then you can see that when you do beta of f compose alpha with something, it becomes f of a. And when you do it with, if you do the gamma, you get the kind of like derivative of f times a. And again, like there's no magic here. It's just straightforward calculation. So we can use this kind of like, you know, this beta and gamma to take f triangle f prime and rewrite that, you know, using like, you know, this beta and gamma. And now we can take our formula and rewrite it, the red formula, and write it as the yellow formula. And this yellow formula, if you can remember the kind of like, you know, the Scholarization, it really looks like, you know, a little bit like an isomorphism here. So this is kind of like, you know, we're very closely there, but the one thing that's like still bothering is that there's this alpha comma 1 that's kind of like on both sides. So that's what we're going to eliminate next. So what we're going to do here is we're going to take the formula that we just had. We're taking a equals 0. Then we're using the fact that, like, you know, alpha 0, 1 is the identity, and now we end up with this kind of thing in yellow. So it took a whole bunch of steps of kind of like, you know, like pounding our formula into this variable free form. But what we have done now is something like that's pretty remarkable, because what we have shown is that alpha and beta triangle gamma are mutual inverses. So we have shown that there's a like, you know, an isomorphism here. And just to get like, you know, make sure that we haven't lost anything, we can recover our previous formula from this one by just instantiating with f equals f compose alpha comma 1. So there's nothing really that gets lost by going to the like the really the last version. All right, so this is where we're at. So we started with the dual numbers property. we reduced it to this kind of cryptic looking formula with F and alphas and betas and gammas. But what this really says is that alpha is a isomorphism between the pair of real numbers and a function from epsilon to d. And that's kind of great. Because what we can do now is we can take this as the axiom for differentiation. All right, so we just say that that we have this isomorphism, and then we just take that as an axiom. And then we define what differentiation is by just saying it's gamma of F composed alpha A comma 1. Now, by now, you will probably think it's like, what is going on? I mean, I don't understand anything anymore because it's all kind of like symbol soup. Which is great. That's what I like. There's no intuition required anymore. I don't want to have any intuition. I don't want to think about kind of like graphs and lines, because maybe that works for a two-dimensional graph. But what if you have a function, for that has 1,000 dimensions? Now you have no intuition anymore. So better to kind of throw the intuition in the garbage can right from the start. So I love this. We just have a new axiom. Where we state that there's this isomorphism between pairs of real numbers and functions, and then we define differentiation in terms of these functions. Now, what we can do now, once we have defined this axiom, we can do some other manipulations. We can do three things. We can take the right-hand side, b comma b equals something, and we can substitute that into the left-hand side. We can take the left-hand side, f equals alpha b comma b. We can substitute that in the right-hand side, and then we can use the fact that since this is a unique thing, and we can use uniqueness. So basically, from this one formula here, we get three formulas for free. So the first one, as I said, we just substitute f into the right-hand side. Then we're we're doing the other way around. And then from uniqueness here, we get this, which is really micro cancellation. So I went a little bit quick, but we're running way over time. So what we get is here three tasty free theorems that hold for these functions. And if you look at them, they you can still remember, or you can beta is really just projecting the first element, gamma is projecting the second element. We have micro cancellation. And then we have an interesting thing there is that every function can be written as a pair of two values. And what we can do now is we can compute what beta and gamma are. So previously we defined what they were, but now we can just use the properties from our axiom to just compute what they are, and the properties we get the definition in some sense for free. And then we can also show that our previous dual numbers property holds also by just using the definitions here and these properties. So this makes the circle complete, right? So what we have shown here is that the dual numbers property is equivalent to this axiom that we've shown, the axiom going back here. So the dual numbers property is completely equivalent to this. All right, let's go here. So what are the lessons here? Well, the trick here that I'm really using, and what the people that are doing synthetic differential geometry do, is that you define your abstraction via a universal property. So you define it with this mutual implication. So you define B to be the unique value such that P of A comma B holds. And it could be that P of A comma B is an isomorphism. Here it could be something else. Then from this formula here, you get substitute left and in the right hand side, whatever, you get all these free theorems, and now everything becomes symbol pushing. So that's kind of like, you know, super cool. This trick actually is got like a very old trick. If you look at the like old squiggle stuff, that's what we did there all the time. I saw Jeremy Gibbons is in the audience. He will probably have a big smile on his face because, you know, this is what we're doing, like have been doing for decades. People in category theory do this all the time when they can define stuff using universal properties. Yes, it's a really neat trick. So if we can put this now next to the like, you know, the syntactic differential geometry, where I said we are simplifying, you can compare the two isomorphisms or the two values of alpha here, signatures of alpha. And you see that in our case, we have just like, you know, like real numbers and dual numbers, where in the syntactic differential geometry case, there is like, you know, there's a more recursion, right? Because like R here is like, this looks like these two sides are isomorphic. So it's like a very complicated domain equation. Like, you know, the pair of R comma R is isomorphic to the functions of infinitesimals to R. So this is kind of like a really complicated recursive definition. And that's why, you know, you have to get like adjust your logic. It's kind of the same thing when you want to get like, you know, a reason about recursive functions or recursive domains, that you have to get like, you know, restrict yourself to continuous functions. So always when you have these things, you have to put in some restrictions. So that's not surprising. Now, another thing is that when we only talked about univariate functions here, if you go to functions with multiple arguments, you have to get like, you know, introduce multiple epsilons, because otherwise you cannot distinguish like, you know, the perturbations for the two different parameters, or if you have n parameters. And if you want to do higher derivatives, you also need like recursion and multiple units of perturbation. So that's the reason why in differential geometry, syntactic differential geometry, they have this recursion going on. And with dual numbers, we cannot do this. With dual numbers, we can only get first order derivatives and only get like derivatives of functions of a single argument, because if we do multiple ones, we get this perturbation confusion. And of course, we can fix all this by extending dual numbers. But first I want to show you here, like, you know, if you want to learn more about this SGD, you can look at this thing here, like John Bell wrote, like, you know, a very, like, you know, enjoyable introduction to this, where he explains this in more detail. If you want to get, like, you know, do higher derivatives, as I said, you need recursion. People in Haskell have figured this out. Like Jersey has done this for a long time. And you see here this data declaration up there that uses recursion. So it's kind of like nested dual numbers. This will allow you to do higher derivatives of kind of like, you know, univariate functions. And you see that there, the kind of df is from a to a, so it gives you kind of like higher derivatives of univariate functions. And then Perlmutter and Siskind, they got like have been writing about differentiation for a long time. And if you want to do higher order derivatives with multivariate functions, you have to kind of have nested dual numbers that become trees. And also you use laziness. So again, like, you know, this is all kind of like, in some sense, you're representing this recursion that's inherent in the this isomorphism for SGD. All right, and now I want to get, like, I think I'm over time, so I'm going to get, like, you know, finish here. Some people, like, you know, traditionally have not liked infinitesimals. For a long time, for centuries, mathematicians have really despised infinitesimals. And it was this guy, Bishop Berkeley, that started this whole trend of bashing infinitesimals. And that's why we got, like, so he's the reason that we have limits, that we are kind of torturing our high school students with limits. because he was kind of like saying that these infinitesimals are really got nothing. They're like, they're crazy things. And they kind of like, we've seen, they got like, lead to contradictions. But you have to just be got like a little bit clever to kind of avoid these contradictions. But just for kind of like, last thing here is that we can define another way to define differentiation. So if we got like use this universal property here, and it looks got like, a little bit weird with got like, G's and F's and deltas. But if we define this property here as an axiom, then we can define that the derivative of f is kind of like, this delta f of a comma a. And then we don't need infinitesimals. Since we're kind of like defining this as an axiom, the proof on the right is just got like, an indication that it's not kind of crazy, right? If we would have infinitesimals, we can prove that this thing is true, that, the derivative of f is actually delta f of a comma a. Again, we're using micro cancellation here. But again, like, we can kind of like, take this as our axiom. And then the great thing of that is that we can now compute derivatives without using infinitesimals. So you can kind of like, if you kind of like look at one of the theorems that follows from the axiom, it shows that if you can prove that these two terms there on the top there on the left of the implication are equal, then the derivative of f equals g of AA. And here's like, an example of a derivation where we're showing the sum rule using this. Again, like there's no infinitesimals inside. Now, the downside of this axiomatization is that it's not kind of like, we cannot translate it into code. So that's kind of like, so it's nice from a mathematical perspective, but with dual numbers, we could directly translate it into code. Here, there's nothing really that kind of allows us to kind of write this in code.